So today we're gonna take, we're gonna continue the rectification. So in half-wave rectification or half-wave rectifier, we have only one diode like this, and here is the load, our load, and here is our source that is AC, and you want to convert it into DC, and the output or the voltage on the load here, VO or VR load, was basically for the ideal voltage model, let's say, it would be the same as the input in the positive half cycle, then zero, then positive again, and so on. Okay, so basically the input voltage was changing in polarity. In positive half cycle it's upward, in negative half cycle it's downward, or positive and negative, and also changing in value. But the output now has only one polarity, upward. The current is flowing in that direction only, and it's positive. There is no current flowing in the other direction, only that one. Okay? When there is current. In the negative half cycle, there is no current. And we found that VDC or V average of that signal, the output signal, is equal to Vmax over pi. This is Vmax. This is Vmax. Okay. Vmax over, Vmax over pi, yes, divided by pi. Okay. One problem with that circuit here is that we just lose half of the input. So half of your power is just lost. So we pass this is 50% of the input power. The other 50% is just lost. They are not passing. So the efficiency here is, the maximum efficiency is 50% in power, the transferred power to the load. So the load, because it only needs DC, with this circuit, the half-wave rectifier, we couldn't pass the negative portion of the input. So the benefit that reaches the load in the form of power, we can say, is only half of the input power, half our source. In this lecture, we're gonna, see or examine another rectifier that can also work or invert, we can say, the negative input into and convert it into positive. So we can get benefit from both half cycles. Okay, and increase our efficiency for the output power. So let's do that. So our first modification for this circuit is called bridge full wave rectifier. Bridge full wave rectifier. As you see here, basically we have now 4 diodes, not only one diode, so it's more expensive in that terms. We need that transformer for both bridge full wave rectifier and also half wave rectifier if the input in the negative or reverse is much higher, or is higher, just higher than the 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 breakdown voltage of the diode. Okay. Or if we need to step it down because it's very high, okay, maybe one of the diodes will break. Okay, so we may need to step down the voltage. So this transformer may be, it's not, it's optional based on your application, may be required for the following reasons. Number one, to step down the input voltage so that either, or maybe both, none of the operating diode breaks. Maybe the input is too high and each element in our circuits have maximum power to hold, otherwise it will break. Or maybe the input is not that high that to break the diode, but it may turn it on in the reverse, or to avoid turning on the diodes in reverse. If you have one of these conditions or even both, then you have to have a transformer, okay, to step down the voltage. How to step down the voltage in a transformer? This is very, very simple. So if you have an input like this, so let's call it V1, and you wanna, this is V2 here, N1, N2. For a step down, that means V2 is less than V1. So you have to have N2 less than N1. That's it. Okay. Okay, so let's see how this circuit is working basically. Why it should be better than the other one, the half wave rectifier, which has only one diode, okay, which is an advantage basically. So let's see. Okay. So I will assume here there is no problem. Okay. The operating power of the diode, the input will not provide very high power, much higher than the diode's operating power or maximum power of operation, or the reverse, the breakdown voltage of the diode is much higher than the big reverse input voltage. Okay, so I just put 1 to 1 here, but just for analysis, to make the analysis easier. Okay, so whatever in here will be transferred exactly to here. Okay. Okay. So let's start our analysis. So basically, we have again two cycles. We have the positive half cycle and we have the negative half cycle. So let's start by the positive half cycle. Why? Number one, the positive half cycle. Now we need a kind of copy and paste to draw it again, because it's really tedious to draw it again. So this is very nice. Copy, paste. Yes. Paste again. Okay, that's enough for now. Okay, so in the positive half cycle, you will have positive here and negative here. In the positive half cycle, the voltage of that point is larger than the voltage of that point. So this will be positive here, and this will be negative here. Okay? Now we can see that some of the diodes will be reversed and some of the diodes will be forward. So for example, D3 here, which has a B that's closer to the positive, D3 will be forward. D4 is the same because D4 has its N is closer to the negative. So D4 and D3 both are forward. D1 has N that is closer to the positive, so D1 and also D2 because its B is closer to the negative, so D1 and D2 are reverse. If they are reverse, you can basically assume they are open circuit off because the current in both are zero. So they are open circuit. So we'll do that. To make the analysis easier for us, we will just remove them. We'll remove D1 and D2. Open circuit, so you can remove easily. You can assume for the sake of analysis that they are not there in the positive half cycle. Good. Now we need, you have here a bridge. This bridge here, which is really ugly. Okay, you don't want any bridges when you analyze. Not to confuse yourself. So let's get rid of this bridge. What I am gonna do, okay, I will take this wire, this crossing wire, and move one of them to the other one. So I will move this, I will take this wire here. Just imagine this. Imagine this is a real circuit, and I will take this wire here, okay, and move it in that way. So this is number one, number two here. So let's do that. Good. Okay, so we remove that guy, and also that guy. And now we will take that wire and draw it here. Just flipping its location. Then you can remove the older position. If this is not clear, please let me know. This is an important step. I want to make the shape of the circuit, something that you feel familiar with. That's my point. So there is a bridge. I just, remove this bridge. I will just move the wire in the other direction, so or another place in the circuit, so that we don't have these bridges anymore. Okay. Please, if this is not clear, especially the last step, you can also ask in any steps, any other step. Okay, that's good. So let's do another. It's really still looks ugly. Okay. So I will, just move this wire a little bit down here. So it's you can draw it. It'll be very easy, not so hard. Okay. This is D4 now. This is the ground. Then this is the resistor, or L. This is VO. Okay, and this is D3. And in all these drawings, Positive, negative, positive, negative. Okay. Any question on that? This is number 3. I'm just playing with the shape of the circuit. It's still the same. All these elements are in series, so I can still make another adjustment. So this is number 4 now, and the last one basically. What I'm gonna do, I'm gonna move this guy here. I'm gonna move this D4 and bring it with D3 in the upper branch. So we have D3, and this, when this guy moves backward like this, its B will be in that location and its N will be towards the resistor. This is D4. This is the resistance, and this is this is VO. And again, this is positive, this is negative. And since we have 1-to-1 turns ratio of the transformer, just to make the analysis easy, to make you understand fast without any confusion. So this is V input, exactly V input, because the transformer ratio is 1-to-1. Of course, the transformer has no meaning because the ratio is 1-to-1, but this is just for easy analysis. In real case, it will not like this. You either use it, and in that case, N1 will be different from N2, or you are not using it. So V input will be directly connected to the bridge. Good. Now we have 2 diodes in series with a resistor, and there is V input. And both diodes clearly are forward, just like the half-wave rectifier, but with 2 diodes. So this is just exactly like the half-wave rectifier, but instead of having 1 diode, we have 2 diodes here. Now we're gonna ask the question: what is the condition on V input to turn both diode on? So each one to turn on needs a 0.7 volt. Okay. So what should be the value of the input voltage to turn both diode on? Any idea?
It's going to be anything above 1.4 volts.
That's right. Yes. So we have 2 conditions again. If Vn is less than 1.4, okay, then both D1, D2, they are forward. I'm sorry, D3 and D4. I'm sorry, D3 and D4. They are forward but off, because to be on in forward we need 0.7. And in that case, ID, this is ID, equal to 0. So VO, which is equal to VRL, equal to 0 as well. Number 2, if V input is larger than or equal 1.4, no, now they will be on. Both D3, D4 are on. So VD3 will be equal to VD4 equal to 0.7. This is VD3, 0.7. This is VD4. VD3, VD4. So by Kirchhoff voltage law, Vn equal to VD3 plus VD4 plus VO. So VO will be equal to Vn minus VD3 minus VD4. So VO is equal to, this is 0.7, this is also 0.7. So Vn minus 1.4 volt. And let's sketch that here before going to the negative half cycle. So when the input reaches 1.4, let's assume this is, for example, the 1.4 point. This is again a sketch. You can choose any point, just a reasonable one. Okay. Then this guy will turn on. So we have again regions at which the diode is on, and the other regions that the diodes are off. When the input is less than 1.4, both diodes will be off. So this region here and this region here, the input is less than 1.4. So the output is 0, which is VR. But in this region here, from that point to that point, all these values are larger than 1.4. What will be the output? The output will be Vn minus 1.4, this equation here. So let's do that. So let's start by this point. This is 1.4. I will subtract another 1.4. So again, the voltage of the output will be 0. For example, we have here 2. So 2 minus 1.4, it will be 0.6. Here we have the maximum. So this will be Vmax minus 1.4. And you continue the same way. So you will have that shape here, which is exactly this one. Exactly. Just cut it from here and put it in VO. And we finish the positive half cycle. By the way, so far so bad, not so good, because in the original half-wave rectifier that we are trying to modify now and increase its efficiency, the maximum voltage was Vmax minus 0.7. Now it's Vmax minus 1.4. So far so bad, not so good, compared to the half-wave rectifier. But the difference will appear now when we take the negative half cycle. Okay, let's go to the negative half cycle. Okay, now the negative half cycle. Okay, and in the negative half cycle, remember this. If you have an input and you assume always this is positive and this is negative, so the direction is always like this. So in the negative half cycle, this guy will have a negative values. But still the direction is that way. And we said that we can do the opposite. We can invert the direction, making the negative here and positive here. But now the values will be positive again. Good. And that's what we're gonna do now. So basically, this is negative and this is positive. So we flip the polarity of the battery. So we must flip also the values. So in the negative half cycle here, we will not deal with this guy anymore. We will flip its values. So we're gonna deal with, this is its inversion. It's a negative all the time, so we're gonna draw its inversion, which is positive all the time. And let's call it V input dash or V input prime, whatever you call it. Okay. So here you have a negative, here you have a positive, which is forward and which is reverse. Anybody have any idea? Which is forward, which is reverse? 1, 2, and yes, 1 and 2 will be forward. Yes. So the N terminal of D1 is closer to the negative terminal of the battery. The B terminal of D2 is closer to the positive terminal of the battery, and the opposite for D3 and D4. So we have the opposite case basically. So here D1 and D2 will be forward, but D3 and D4 are reverse. Reverse mean open circuit. You can model them as open circuit. That's what we're gonna do now. So we're gonna remove D3 and D4. Good. And this is, the first modification. Good. Still, again, it looks ugly. Okay, so we want to modify it. What I'm gonna do, I will take this wire against the bridge. Okay, this wire here, this wire, this bridge. Okay, and move it away from the cross section to remove the bridge. So I will take it and move up. When I do that, the ground will be in the up direction. So RL will be flipped. Okay? So this will be converted to the following, shape. We'll keep everything the same. Yes, and now this guy has been, So this is D2. And now we will flip this wire upside down. So this is RL, and this is the ground. It's flipped now, okay? And also when you flip this wire up, this guy D1 will be in that, what looks like in that way. Okay, so this is D1. Okay, and remember, VO is from the ground to this point. The ground is here, and this point now become here. Okay, and don't forget the polarity, negative and positive. Now let's check how the current will flow in that circuit. The current always flow from the positive terminal of the battery to the negative terminal of the battery. So we start from here. And before continuing, this is a very valid direction of the current through a diode from B to N. So we are good. Then it flows from this point to the ground. From this point to the ground. Then continue to D1. And this is also valid because when the diode is forward, the current must flow through B to N and continue to the negative terminal. We can do the same here also. So we start from the positive terminal, valid because from B to N, then from up to down, continue, cross the bridge, D1 from B to N, valid until you reach the negative. we are saying that this should be a full wave rectifier. And yes, it's a full wave rectifier now, because in the negative half cycle, there is a current flowing in the resistor. But is it the same direction as the current that was flowing in the resistance in the positive half cycle? Let's check. Let's go back to the positive half cycle and see. So in the positive half cycle, let's follow the current direction. Flows from the positive terminal to the negative terminal. From the positive terminal, very valid because from B to N in D3. Then again from high to low, from this point to the ground, still in the same direction. Then continue, cross the bridge, flow in D4 in that direction from B to N is still valid, and then continue until you reach the negative terminal of the battery. So we succeeded in having a current in the negative half cycle in the same direction as the positive half cycle. So let's now check the polarity or the sign of the voltage, VO. VO, the voltage across the resistor is always in opposite direction of the current. So in that direction it's positive, and in that way, like what I'm drawing, from up to, from the ground to this point. Or this point has a voltage larger than the ground. Let's check the same for this circuit here. So again, the current is flowing from this point to the ground, just like the negative half cycle. So the voltage V output is from ground to this point, which means that this point has a higher voltage than this one. So same current direction with same sign, of course. Same voltage direction with the same sign, of course. So we are very good. Now we see the difference. Okay? Okay. So these are all series. So I will move D2. I will move D1 to be just beside D2. Nothing new. We do that all the time, at least for the positive half cycle, to make the circuit looks good. So this is D2, and when D1 moves it to D2 to the same branch of D2, it will have the same polarity as well, same direction. Then you have the resistor, same output voltage direction, and the ground, and negative and positive. Let's do one more trick. One more trick. We're gonna flip the circuit. Okay? So we're gonna, take this wire, for example, and move it above here. So the positive will be up. And the negative will be down. And let's now compare this one, which we just got from the negative half cycle, with the other one, which we have in the positive half cycle. They are exactly the same. So they will have exactly the same output as well. Okay? So we're going to do the same stuff as well. So we're going to say that if V input, number I, V input dash now, V input dash, V in dash, is less than 1.4, D1 and D2 are off. So ID is 0. So VO is 0. Second case, when Vn dash is larger than or equal to 1.4, D1 and D2 is on. So VD1 equal to VD2 equal to 0.7. So VO equal to, let's do Kirchhoff again. So VM, let's do it, step by step to make it very clear to you. Vn dash equal to VD1 plus VD2 plus VO 0.7 VO equal to Vn dash minus 1.4. Exactly the same equation that we got from the positive half cycle. But instead of V input, we have V input dash, which is just a flipped version in polarity. So let's sketch that. When V input dash is less than 1.4, V out is 0. Okay. When V input dash is less than 1.4, this part and this part, the output is 0. I'm sorry, it looks ugly, but that's fine. Now, when V input dash is larger than 1.4, in that region from here to here, VO is equal to V input dash minus 1.4. So take any point and just subtract 1.4. So this is 1.4 minus 1.4 will be 0. This is 1.4 minus 1.4 also be 0. This is V max minus 1.4, so it will be V max minus 1.4. So basically you will have something like this. And this thing here is exactly this thing here. Okay, so this is now full wave rectifier. And now so far so good. Okay, now we beat completely the half wave rectifier. We gain, another 50% conversion. So we are close to 100%. Except for this, this period of 0, which doesn't really matter because usually Vmax is very high compared to 1.4. So this you will not just like what we saw yesterday in the lab. So they don't have really an effect, a much higher effect on our output shape. Basically, if this is an ideal diode, and and you are wanna just neglect this 1.4, you will have exactly something like this. So the positive passes perfectly, and the negative flipped, but perfectly. I mean, -1 will be +1, -2 will be +2, minus Vmax will be positive Vmax. Okay, that's very nice. That's very nice. So let's now take another circuit. Any question, guys, on the full wave rectifier? Any question? Here is full wave rectifier again. Any question, guys, before we go forward? Not reverse. Any questions? Yes.
I was just saying we're good so far.
Okay, thank you. So let's go to another circuit that's supposed to have better output than the half wave rectifier. Okay, it looks a little weird, but this is what the name suggests. It's called center tape full wave center tape rectifier. So this circuit basically needs a special type of transformer called center tape transformer. This transformer provides you with some extra ground connection, and it has very useful application. This is one of its applications. So we have here a forced ground at the center of the, this is called the primary coil. This is called secondary coil. Any transformer has two coils, one to the input, one to the output. Each one has its own number of turns. The one to the input is called the primary coil, the one to the output is called the secondary coil. For the center tape transformer, this secondary coil is halved in two halves with a forced ground in the middle, in the center. Just by looking at this circuit, we realize that it has advantage over the full wave rectifier. The bridge full wave rectifier. Any idea what this is? What is the advantage of this circuit over the other one? Very simple. How many diodes here? Yes, yes. So we have only two diodes. So compared to the full wave rectifier, bridge rectifier, which has 4 diodes out there, so we 50% reduction in the number of the diodes. But the transformer here is a must. We must have not even any type of transformer. It must be center tape transformer. So the transformer here is a must. You must use center tape transformer. Even if the breakdown voltage of the diode is larger than the maximum reverse input voltage, even if the operating power of the diodes when they are operating is higher than what the input power will provide to the diodes. So you might have a situation in which you don't need transformer, but because you need to you want to implement this center tape, this kind of rectifier, you must again have this transformer, because it's the operation of this circuit is based on the presence of center tape transformer, even if it's 1-to-1. So let's analyze it. Okay. So again, let's start by the positive half cycle. One good thing about this is it has, less complications than the other one, as we will see now. So in the positive half cycle, we have positive, negative. And this is, if we have 1-to-1, this will be the input. Because of the ground, this input will be halved. So this will receive the input over 2. This will receive the input over 2. The ground to the negative can be considered positive. And positive and the negative in voltage difference means some point is higher than the other point. And the ground to the positive can be considered the negative. So basically, positive, negative, positive, negative. It's a relative stuff. The ground to the positive is just a negative, can be considered negative, relatively, and the ground to the negative can be considered positive. And this is what, by the way, what the center tape is doing. He creates such kind of, of polarity, you can say. Now, D1 is forward. Basically, it's B is closer to the positive terminal. And D2 is reverse. its B is closer to the negative terminal. So we can, you know, modify the circuit or redraw it in that way. Open circuit here. Then we have here the center tape. We have VO. And D1. Positive, negative, positive, negative. Now let's see how the current will flow. The current flows from the positive terminal. And before continuing, this is valid direction, because when this guy is on, it only allows the current to flow from B to N. Then it comes at this node. This is open circuit, so all the current will go to the resistor. And notice the direction. It's flowing from, let's call this is right, or right to left, from this node to the ground, from this node to the ground, and continue to the negative terminal. So basically, we can remove the lower half. It's just a model. And so this is basically number 2, number 1. Okay? So it's very simple. Now we have a very simple circuit. One source, one resistor, one diode. Again, when V input over 2, and remember the source now is V input over 2, not V input, is larger than 0.7, not 1.4 like the bridge. Okay? Let's start by the less than, to be consistent. So less than 0.7, so D1 will be off. It's a forward but off. So ID is 0. So let's do the Kirchhoff. So Vn over 2 equal to Vd plus Vo. Vo is 0 because ID is 0. Okay. Yeah, so just, so VO is, we don't need to draw, this is actually your homework, to draw to sketch the voltage on the diodes. So VO is equal to 0. Number 2, when Vn over 2 is larger than or equal to 0.7, now D1 will be on, so Vd is equal, Vd1 is equal to 0.7. So by Kirchhoff here, VO will equal to Vn over 2 minus 0.7. So before continuing, this is better or the bridge for wave rectifier? Any idea? Let's compare them. So VO is equal to Vn over 2 minus 0.7 for the bridge. In the positive half cycle, VO is equal to Vn minus 1.4. Yes. So so this is better actually. The output of, yes, the cut is 1.4 and here the cutting is 0.7, but usually this 1.4 or 0.7 is very small compared to the huge amount of Vmax. So if we neglect here the 1.4, Vmax in the output is, I'm sorry, VO will be equal to, the VO maximum is equal to V input maximum. But this guy, V out maximum is equal to V input maximum over 2. For the same input, you have this is actually bad. This is not good at all. Okay, but we can fix this using the transformer. Don't forget about that. Okay. So let's draw that. So this is V input, but remember we need V input over 2. Okay. If you have a sine wave, sine theta, for example, and you draw sine theta like this. So half sine theta, and this is 1 and -1. Half sine, since the frequency is the same, half sine theta will be something like this. And this is half minus 1. Okay. So V input over 2 is actually something like this. If this is V max, so this is V max over 2. And we are saying if V input over 2 is larger than 0.7, then will be, you know, on and off. So we need this point here. So let's assume this is 0.7. When V input over 2 is less than 0.7, which in these two small regions, the output is 0. Then between these 2 points, or when V input over 2 is larger than 0.7, the output is V input over 2 minus 0.7. So take any value from these values and subtract 0.7. So it will be something like this. And this point here is V max over 2 minus 0.7. Now let's go to the negative half cycle. Number 2, negative half cycle. In the negative half cycle, you have negative here, positive here. Now you change the polarity of the input, you must also change the values. So I'm gonna draw the same input, but flipped. With the original curve, this solid curve here is the original input, but now this is, let's call it V input dash. Good. So this is V in dash. The ground to the negative is considered the positive. The ground to the positive is considered the negative. Again here, V input over 2, V input over 2. Now, which is forward and which is negative? Now, D1 is reverse. And D2 is forward. So we can basically remove D1, it's open circuit. And before continue forward, let's check first the current direction. So the current flowing from the positive to the negative. This is very valid because it's flowing through B to N. A branch. This is open circuit, so continue in that way to the negative. So it's flowing again from this point to the ground, just like what we have in here, from this point to the ground. So you have, in the negative half cycle, you have a current now. And it's flowing, it's a positive current and flowing from the same, in the same direction for the die. So the voltage will have the same polarity, positive and negative. And basically you can, you know, just remove, just a model, remove this upper half of the circuit and just to continue with the lower half. We like our ground to be, you know, in the bottom. So I will take this branch and move it, flip it around. So this is number 1, this is number 2, this is number 3. This is actually the last modification we're gonna do. D2. This is R. This is VO. And this is, most of this is negative, which is exactly that circuit, exactly the same. Okay, with same analysis as well. So, and this is V input dash over 2. So we're gonna say number I, when V input dash over 2 is less than 0.7, D2 is off. So VO is equal to 0 because I is equal to 0 and I multiplied by R is equal to 0. Number 2, when Vn dash over 2 is larger than or equal to 0.7, D2 is on, VD2 is equal to 0.7. Now let's do Kirchhoff. So by Kirchhoff here we can say that Vn dash over 2 equal to VD2 plus VO. So VO is equal to Vn dash over 2 minus 0.7. And let's draw that. This is V input dash, but we need V input dash over 2. V input dash over 2 is less than 0.7, that's section and that section. The output is 0. And when V input dash over 2 is larger than 0.7 from here to here, the output is V input dash over 2 minus 0.7. So take any value from these values and subtract 0.7. This is of course exactly like this. Sorry. And again, this one here is exactly like this one. Okay. Now one might say, this may be equivalent to the half-wave rectifier. No. Because here we can fix, yes, because yeah, I know that you are saying this because this is Vmax over 2, not Vmax like the half-wave rectifier. But this can be fixed. If the transformer ratio is 1 to 2, this is fixed. If the transformer ratio is 1 to 2, then this guy will be Vmax minus 0.7. This guy will be Vmax minus 0.7. So still, the efficiency is doubled than the case of the half-wave rectifier. Okay. So let's now compare the bridge rectifier and the center tape rectifier. So we're gonna compare them for some characteristics. Yeah, number 1, number of diodes. Number 2, transformer necessary or not. Number 3, Vmax in the output. Number 4, yeah, VDC. We didn't mention this, not anyways. Yeah. Okay. And we're gonna put bridge. Then here center tape, full wave rectifier, but in 2 cases, with 1 to 1 and 1 to 2 transformer ratio. Okay. For the bridge, we need here 4 diodes. We need here 2. We need here 2. Whatever the transformer. The number of diodes doesn't depend on the transformer ratio. Is a transformer necessary in bridge? Maybe. Maybe necessary. But it's not requirement. So this is maybe. We may need to step down the voltage. Here, it's a must. You must use transformer, center tape transformer. And by the way, using a transformer is not that good because if you need it, you must use it, of course. But it's bulky. For example, the adapter that you have at home that converts from AC to DC, by the way, and uses some circuit like this, with this principle, it's bulky because of the transformer. The maximum in the output with the bridge, it was Vmax minus 1.4. Here it was Vmax over 2 minus 0.7. If we ignore the 0.7 and 1.4, of course, bridge beating this guy. But for 1.1 to 2 center tape transformer, this will be Vmax minus 0.7. Better than the bridge. But again, this 0.7 and 1. It's really very small, usually very small compared to the input voltage maximum. Now the DC, this guy. Of course, I didn't mention this. So for the half-wave rectifier, we have something like this. And VDC is equal to Vmax over pi. So for the bridge, if we take one cycle, this is 2 Vmax over pi. So 2 V maximum over pi, doubled. Here, if we compare the of course ignore the 0.7, it will be 2 Vmax over 2 over pi, Vmax over pi. Same as the half-wave rectifier. But this can be fixed now using the transformer. So this will be 2 Vmax over pi again, just like the bridge.